this notion was developed by people that overlap with people I just showed. In a sense, I myself did something. Oh, I think I have the wrong slides here. I'm a bit confused here because I thought I cut that part out. Check if are these the right? No, I have the wrong slides here, so sorry. Is this the wrong year or what is that? Yeah. Oh yeah, this is like from last year. Yeah. Okay, good. So it comes from the same mindset of using oscillators to generate timing and use coupling to achieve particular relative timings. It's has a little bit more complicated history that I didn't want to all review. And it's a core idea that is really still very valid, although some of the other things have sort of fallen by the wayside in the meantime. It's a nice review paper from 2013 that I'll be showing figures from. So there is some motivation why that would be biologically possible. Frankly, that isn't really so deep. But it was actually developed as an approach to learn from human movement. So Auke Ijspeert is the lead author here. Auke was involved, and Stefan Schaal was sort of the head of this kind of direction, working at that time in California. They had this idea that you would be learning from emulate human movement, so be able to move like a human, for instance, making these very smooth kinds of movement profiles that Lei Zhang presented in his lecture. And that will be useful for interacting with humans, but it will be also useful maybe to copy some of the skills from humans. But then you would want to generalize that, so learn just the general shape, but then be able to make a movement to a location that wasn't in your learning material. So make a movement to to intercept the ball, for instance, that is now one particular location that isn't exactly in your training data set. And this, what I'll present to you, solves that kind of problem. That's, in a sense, a general problem, because you might often have some constraints on how to generate movements that, for instance, have to do with control. But then you also want to make a particular movement that reaches a particular target, a particular role, for which you don't know exactly what the shape these constraints take, and you want to integrate these two. So I'll take you through that, and then you'll see what I mean. In the end, I think you will understand more clearly what I just said. So the idea here is not quite as sophisticated. It's not like a limit cycle. What you're actually using is a harmonic oscillator. It's a critically damped forced harmonic oscillator. So this here is a harmonic oscillator. There's a second derivative. There is the variable itself. There is the first derivative, and there's a forcing function. It's written in a somewhat funny way for specific purposes. It's actually kind of easier to understand it as or it depends on your preference. It's written down in these papers as two first order equations. I have another variable z, that's y dot, and then y dot is replaced here by z. Now you know that if it's a harmonic oscillator, it has a stable fixed point. When the drive is 0, then this has a stable fixed point. It's written so that you can see that the fixed point would be where y equals g and y dot or z equals 0. So that will be where you have 0 velocity and you're at the resting level of that oscillator, right? An oscillator is like a mass spring, a damped mass spring system. So when the mass stretches the string to its equilibrium length and the viscosity has made the dampened out any kind of oscillations, then the spring rests at its resting state, and that's an attractor. That's a particular elongation of the spring. That will be the position, the goal point, and it has 0 velocity because of the damping. So the idea will be that by setting this fixed point attractor to the right distance where the variable would have, reached a particular state from its starting position, which would be 0, then you would know that you can arrive at that trajectory, and by making the damping right, you would smoothly arrive there, like in a overcritically damped trajectory. And through the forcing function, you can vary the exact time course how you get there. But what will make sure that in the end of the movement, when you're near that goal point, the forcing function is 0, so that they ultimately go to the attractor. And that would be the generalization. By making the attractor, you could move the attractor to whatever desired location based on, for instance, predicting where the ball will land. And then the forcing function will make the time course that you have learned. And so these forcing functions were built, these are the primitives, were built from templates. Here, this it's like a little Gaussian bell-shaped trajectory. Think of C and X as time. I'll explain that in a moment. It's some funny notation of time. So CIs are different moments in time. See, there's a grid of times, and around each of these times, you have a little Gaussian time lip and some scaling. And then these different primitives are weighted with a weight W normalized to make the forcing function. So the different primitives contribute differently. They're also called kernels here, and the kernels would be activated at different moments in time. So there's real like a score that is a discrete set of times at which you bring in one of those contributions to the forcing function. In that sense, this is a non-autonomous kind of dynamics. There is some absolute time score being kept. So on a computer, no problem, right? You have a computer clock and you say, oh, I'm now at 300, I'll activate the score. That's a question of how that would be biologically done. Now the time is encoded in this funny way. This X is called a phase. So this is an exponentially decaying variable. So instead of keeping track of time, they keep track of where that variable is for some convenience reasons. It's just a recoding of time, right? You have a linear differential equation, has a unique solution. It's really recoding because when the movement starts, they reset this variable to start at 1, and then this decays. So it's not continuously running, so you have to sort of set it, and now it keeps track of where it is in the movement. This is what they call the canonical system. So there's a sort of an external timer. This is sort of the timer that tells everyone to be aligned. Now that tells everyone, we're here at this much % of the movement. Yeah, and so the X that was here, that is that X, that timing variable X, and that's how you see that the C correspond to different moments in time, just expressed in this funny rescaling of time, where time goes from 1 to 0 rather than from 0 to some value. Actually, this time, of course, goes to infinity, and you have to have some cutoff when you consider this done. So the last trick is that the forcing functions are actually multiplied with these two terms. So this term here makes sure that when X is small, that will be at late times, the forcing functions go to 0. That's how you make sure that at the end of the movement, this attractor determines the behavior and the forcing function no longer matters. So you go to that attractor. And the other is that when the variable, so y0 is the initial position, and so that this is scaled with the amplitude. So if you have a large amplitude, you will multiply these forcing functions with more larger term than a smaller term. That's how the deviation that you induce in the velocity will matter even for a very large movement for which the oscillator itself, the spring itself, contributes very large force. So the amount of forcing of these variables is in a constant relationship to the amount of forcing that comes from the other parts of the dynamical system, from this part of the dynamical system. See, here's all the G minus Y term. Good. Here an example, academic examples of these dotted lines that are barely visible, like here and there. You see that would be a desired movement that you have to track. and the solid line is how the system tracks that. So it did that by fitting the weights, and I'll explain in a moment how that works. So it just shows that it works, and this is an example in 2 dimensions. No, the same example, just to show you this is the concrete contents of that makes that work. And so toward the end of the movement, see there are these kernels don't really contribute anymore. I already explained that, and I want to skip that. And so I just want to say that one can use one gentle phase and drive from that many different kinds of movements. That's sort of the idea. So it's the central timer, and everything else is then generated from that. That's a biologically valid idea, I believe, that we also embrace. So here, this example I wanted to show to give you an intuition how this works and what the logic of that is. And then I'll briefly show you the learning rule, and then we're actually pretty much done. So this illustrates what happens here in the movement. So you're initially sitting here, the time goes this way, and so you want to end up here, and there's a particular time course that you want to emulate. And also the important thing is you don't want to go to the target just like that. You want to really create a time course that has some desired properties that you have from some learning examples. And so initially you have an attractor here, and then what happens is that this forcing function now moves effectively the attractor around. You see now the attractor is somewhere here, and now it's somewhere here, and now it's somewhere here, and then there. So you could think of that as a vector field. The vector field is really this harmonic oscillator, and the forcing function shifts where the attractor is. There's always an attractor in a harmonic oscillator, right? A damped harmonic oscillator always has an attractor. Initially, it's in the initial position. And then when you add that forcing function, you're shifting that attractor around, and you're not really tracking that attractor, because that will, you could only move it a little bit, right? In our approach in the past, we're always tracking the attractor, and that means we're always close to the attractor. But if you want to make drastic movements of a certain shape, you need to create, some non-trivial time course, and that's done by moving the attractor quite far, like up here, or up here, and the system is not there; it's back there. So what you're really doing is, through that, you're creating a vector field that where the state currently is, the system experiences the right acceleration and so on. That will then lead to the trajectory shape that you are looking for. So why this fancy way of doing it? Why not creating directly a velocity profile for your planning variable that matches the template that you have learned? And the reason for that is that generalization. That is, what you want is that in the end, you end up in a position here that you don't have a template for. That is, you don't have a fixed template to go from here to there with that particular time course. You just have your generic template, and then now your new target position. And what the system can do is it can approximately rescale your templates to take you to the right attractor and really generate, in the end, the right attractor. And thus generalizes that profile. And that is the more general idea. This is here a little bit in these examples that this group generated. It's a little unclear why that is so attractive, because learning these human-like movements, that's maybe somewhat cool, but it's not very dramatically different from just designing these movements. But we're currently interested in these kinds of ideas in control, where you might have the equivalent of templates would be control strategies. You have particular ways of, of initially accelerating and maybe finally braking that are learned to be successful. But then you might want to apply these control templates to situations that you've not experienced in your training, and this would be a way to generalize. So so this mathematical form was really used because one can learn very easily the forcing functions, right? The base oscillator here can be reframed, putting the driving force here on the left and the acceleration on the right. And then here on the right, you only have terms that depend on these dynamical variables, here the y, and that is something that you would have data for from examples. Somebody demonstrates that movement and you record that movement, a human, and then you can estimate what forcing function would have generated that movement. And now you need to learn that forcing function. It was a very trivial thing. You want to minimize the distance between your model forcing function and that observed forcing function. So you could see this is a simple regression of these weights here that minimize this cost function. It turns out that can actually be computed analytically. You can actually compute analytic term of the experimental forcing function that is the weight, the right route. Makes it very attractive, very, very efficient to do that. That's why that was quite attractive. These groups have added other constraints to their systems. For instance, they added obstacle avoidance. That was actually based on some of our original work. This is the obstacle avoidance that we studied, right, in the first part of the course, and that can be lifted to end effector movements. It's actually obstacle avoidance only by the end effector. And to do that, you have to go into a angle space. You have to translate the heading direction into the heading of your hand toward the target. And there's some way to do that, which I'm not going to explain exactly, based here on this kind of notion. And that works. We also published something like that in slightly different notation. This initial position can avoid an obstacle that is behind, that is blocking the movement toward a target. It turns out that we also implemented something like that. And unfortunately, that isn't really what human obstacle avoidance is like. We did an experiment, a series of experiments, this one paper, studying that. And there's a doctoral thesis that was just handed in that finally made a model of these data. And it turns out humans have, they make the obstacle avoidance really by modifying the timing. So they would actually not keep the transport component so constant. So this kind of component constant, just deviated in space, but they actually modify the timing. So you're going more slowly so that you can move away from the obstacle, and then you go fast again so that you reach the target in approximately the same time. I didn't want to go through that entire model, but that's ongoing work. We'll be publishing our results hopefully next year. And that sort of puts the biological realism of this in perspective, but this is still, technically a good solution that would be pushed much further. So the notion is that you could do coordination by making use of this phase variable. So when you have multiple different systems, you could make sure that these different systems all share the same phase value. I don't think they've done much with that, but it is it's a valid idea. So I conclude this very brief excursion into movement primitives that these dynamic movement primitives enable learning, movement styles or some principles of how movement should be temporally organized, while it is also able to generalize then to movement targets for which you have no example movement style. So you can generalize the movement style to new targets. And this is the idea, the part of this literature that has, I think, broad implications and can be used in many different ways. This particular approach is just kinematic, so it doesn't really deal with control. And that's perfectly legitimate for robotics, where, as I'll teach next week, control is decoupled from planning, where you can make sure that your control system can realize any plan within certain constraints. In human movement, biological movement, that is not a good strategy because human arms are soft. Lei Zhang already pointed to that, and so they're soft, which is good, because if we don't have perfect estimate of obstacles and surfaces and so on, we would hurt ourselves and maybe the objects would also destroy the objects. That's why robots are dangerous, because they are very strong and they will destroy stuff that isn't taken into account in its motor planning. And we might hurt sometimes a little bit, but we are never, they're rarely going to break our arm because we are doing the entire control in a much softer way. And that means that if we want to track a desired trajectory, first of all, that we can't track just any trajectory. It has strong limits on its kinematics. But it also means that we do have a control problem. That is, we do have to make sure that we try to accelerate hard initially, because the rule arm will be accelerating less than maybe the command we send to it, and then also try to brake hard. And so next week, I'll talk a little bit about controls like that. The limitations of the DMP are really also, even at the kinematic level, there are limitations from a lot of these special tricks it has. So the non-autonomous aspect of initiating and then terminating, that leads to some problems that we've experienced ourselves when we implemented some of those ideas. So I'm not sure how practical this approach will be long-term. In this much more elaborate form that OBR has and a couple of collaborators, a lot of these problems have been solved, but it's not so easy to visualize. Okay, that's as far as I want to push this. And I close this here.